We are going to look at scattering correction, which is another kind of correction we do in the tomographies when we're talking about neutron imaging. And the outline of this tutorial is that first we look at the cupping effect in neutron tomography, and then we see why, which is that most elements scatter. The scattered neutrons, they add a bias, which we're going to look at, and there is actually a method that we can look at, can use to correct these biases. And finally, I'm also going to show you how to do this within MuhRec. So first you get a tomography, which looks maybe like this. It's not very convincing actually. You can see that there are darker regions in the middle, there are some streaks, and this is really not what you can use afterwards for some kind of quantitative analysis. So the next step would be to check what is the reason. Those of you who have been looking using X-rays, you would say, okay, this darkness depends on the beam hardening, but for neutrons it's actually something else, and that is the scattering. And if you look at some of these elements, you can see that, for example, hydrogen scatters a lot, oxygen, carbon, aluminum, actually most of the, say, normal elements you come across in an experiment, they scatter mostly and sometimes a little absorption. And what is happening with these scattered neutrons is that if you have a parallel beam coming in, you can have some interaction with the sample, and then the main interaction is scattering. That means some of the neutrons, they will bounce around to different places than they are supposed to. And there can also be scattering from the background, the sample environment, etc. And all these neutrons, they end up producing a bias behind the sample, and this bias actually makes this area that you have seen as the darker region in the middle. What we have developed is a method where you can measure the scattered bias, and that is done with the help of a grid with absorbing dots. You can see some dots here, and those dots will be also projected in the image. And then you have the sample in here. And what is happening is, if you have the direct beam, it should be dark, but the scattered neutrons from sample and from the environment, they will actually contribute behind these dots, and that is the bias you will see. The whole correction procedure requires that you have open beam images that include the black bodies. You have sample images with black bodies, and these two sets of images, they're actually in addition to the dark current and the normal open beam that you have. And there are different strategies how to acquire these black body images, in particular the ones with a sample in them. So if you have a round sample, you could say, and particularly when it's centered, you can say that, okay, it's sufficient, a single view, and from that you will get some contribution behind the sample, you will have something outside of the sample, that's fine. If you do a tomography, and in particular if you have a very eccentric positioned sample, or if it's a sample that is very irregular shaped, so for example a statue where some pieces peek out from the central body, then it makes more sense to do a sparse tomography scan. And with sparse, I mean maybe normally you do over 300 projections for your normal tomography. The sparse scan may only have 26 projections. And what the algorithm is doing then is to interpolate, because the scatter contribution is very smooth. And then it's actually sufficient to do something like 25, 26 projections around the sample. And then the correction itself is a revised version of the normalization that you normally do. And you can see here that there are a lot of contributions that are calculated from the black bodies. So from these black body images, you can compute some background scattering contribution, you can compute the sample scattering, and first you have the sample without correction here. You can see it's a little bit darker. and you have the sample with correction here. And the profile you can see at the blue line and the green line here. You can see that this correction is actually pretty remarkable what we have done. And this sample contains water, and we will actually use this one for our tutorial when we use it in MuhRec afterwards. So the impact of this correction is, without correction, you will have a pretty dark central region, and at the boundaries you will see that it's brighter. If you do beam hardening correction, there is a slight improvement, but still you have this cupping effect. Then if you do the scattering correction, you can see it's getting flatter. And if you want to do it really good, then you could even combine the two, including both beam hardening and scattering correction. And the effect, what you can see from this, is that the histogram of this item in the beginning, it's pretty flat and pretty distributed over many gray levels. And the more corrections you add, the closer you get to some kind of Poisson or Gaussian distribution, which you would expect actually. So let's go on and see what happens to our previous sample. If we do this kind of correction, you can see that all the streaks are here, it's darker. And after this black body based scattering correction, you can see that all these effects are actually more or less gone. So this is a great improvement. And now we're going to check what's happening within MuhRec. Here I have reconstructed with a normal procedure, and we see that you have the brighter outer ring and you have a darker region in the center. And yeah, so I had here the sample data, 626 projections, some open beam. Here it's called FL for flat field, DC. And if we go in here, we can see I set the pixel size, which is very important to set correct if you want to get quantitative attenuation coefficients in your reconstruction. Then it was a half turn of reconstruction. I found the center rotation. And in the processing chain, you can see I did full log norm, I did spot cleaning, I did ring cleaning, and then this would be the effect. And as you also can see, is my histogram here is very distributed, as we also saw in the slides before. And now I'm going to add the black body correction, and that is done in the processing configuration. Best you just click on the topmost one here and select add. And then you get this dialog where you can go down and find BB log norm. Press OK. And now we have two normalizations, and that is one too much. So we uncheck this one. And as you can see, there is many parameters to tune this algorithm. So it's much easier to go in config, which I do here. And the first dialog you get is some information. Right now, we have the main option you have to set here is if you want to do a tomography black body or if you want to just do a single view. And in this case, I'm selecting average. And then I go on to BB images. And here I select first the open beam images with black bodies. And then I have to locate them. I have them on the desktop. And then you can see here we have FLBB and open. Then it appears here. Now you have to select a region which includes as many black bodies as possible. So let's select something like this. Press get here, and then you see it turned the green rectangle around all the items here. The next one is you want to have the sample images with black bodies. Again, we click browse, go to the desktop, and then I want to have water BB and open. And here you have to mark a dose region of interest. And in this case, I know in this region, I don't have any sample coming in. So this dose region of interest is similar to the one you have marked before, but you need a second one in this case. Then we do get, and then we have marked up and told about the data. And now we can go down here, compute threshold, and you can see some very tiny white dots. They mark the central point of each of these dots. Sometimes you don't see them because they are too small at this scale, but they're actually there. Then in some cases, it could be that you get troubles finding these dots and it gives you an error. It's not possible to find. Then there is still a way to do it by selecting manual threshold here. And then you have to play with the threshold. Usually 0.1, 0.2 should be sufficient to compute the threshold. And with that, we have set up everything and we can go in here, pressing OK. And now we can start reconstruction. And I already have a slice here. And if I start the reconstruction with start reconstruct, then it takes a little while in the beginning. You can see here the computer is busy. That is when it's reading in all the black body information. And then at some point now you start reconstructing the slices. And then it's the normal procedure as we usually had. So and back projecting, and it's done. And now you can see you have a much flatter profile here. You go from about 4 till 3.6 about. You can also see that this one has improved a lot. It's not that extended as before. And then we can also do a check here. I have saved from previously. Save the two to compare them. So I can click here. This is without, and this is with correction. And you can see here that now the gray levels are pretty homogeneous in here, and in here still you have the white ring. And that ends this tutorial, and I hope you will have use of the black body correction. For that, of course, you need to organize a grid containing these dots. And well, thank you for listening.